Hey everyone, this is our fourth session at Hackaday on quantum computing. I know there are still some newcomers today, but don't worry, we have recordings made for people to look back. So everything is on the Hackaday project. You can find the slides and the recording. So we had 3 sessions in the past. These are the concepts that we covered before. So just to recap, in the last 3 sessions, we talked about some basic concepts for quantum computing. Primarily, the superposition is a main reason for the second and the third interesting aspects of quantum mechanics. So interference is showing the result. So the result of interference is what we see in measurements. And entanglement is another strange thing enabled by superposition that when qubits are entangled, their results are correlated. So those are the 2 main or 3 main things that we covered in the last 3 sessions. If you missed them, don't worry, you can go back to the recording. But those are the fundamental basics of quantum mechanics that we are using in quantum computing. So today we're going to talk about actually how do we make use of the qubits. We've described what a qubit is with some mathematics, and also just conceptually is like the classical bit, but then superposition allows it to be at a percentage, certain probability of being state 0 and certain probability of in state 1. And we can, of course, describe it differently with a graphic view. So here, a graphic representation of a real number. We are all very familiar. When we were kids, we learned that we can draw them in a line. And it's just a real number that you can get different lengths for different numbers. When it becomes a complex number, when we are talking about complex number, we can then represent it in coordinate that will show you both the magnitude and the phase. So that's how we can graphically represent complex numbers. So in terms of qubits, we can also use graphic representations. So here, this is a geometry that we can use, is basically a sphere, to represent this vector, which is our qubit. So it has the amplitudes A and B for the 0 state or the 1 state. And it's just a 3-dimensional, so actually the surface of the sphere is 2D, but it's a sphere, and it gives us 2 parameters. One is the theta, one is the phi here. So on the Bloch sphere, the top one is state 0, and the bottom one is state 1. And then any arbitrary state, you can represent it on this Bloch sphere. So our phi is an arbitrary state, and it has a theta angle away from the z-axis, and angle phi away from the x-axis. So this allows us to write down how to represent the state phi with these angles. So this is pure geometry, and the useful thing that we do this is that the angles now is basically in a polar coordinate, and it can give us these amplitudes A and B. So we just represent the amplitudes with these angles in the sphere. So because it's a sphere, it has all kinds of possibilities. This phi can be anywhere on this sphere, and we will just use a different number for theta and phi to give us the amplitude we want. So if you start with any state, you want to change it, you want to manipulate A and B. So basically, you're just changing the location of this state on the Bloch sphere. So that's how we're doing. And last class at the end, someone asked a question, how do we obtain the amplitudes that we want? If we represent it this way, we can visually realize that as long as we can control the angles, we can get any number of the amplitude we want. So as I described earlier, the 0 and 1 are defined at those two polar positions along the z-axis. And then we can write out mathematically how to find a arbitrary state. So 0 and 1, we know that in classical case, we only have these two options. But then in the quantum case, we have unlimited number of options for a qubit. So 0 and 1 are nothing but two special cases. So classical states are just two special cases for a quantum state when theta is either 0 or 180 degrees. So you can just think about classical bits as part of a complete qubit system. And then we want to know how we can manipulate it just by changing the theta and phi. So geometrically, you can just see that we can use matrices to apply to a 2x1 vector. And we can have a matrix that changes the angle phi and another matrix that changes the angle theta. So that's all, that's it. This is a very generalized method to change qubit states. And people can also call these a universal gate set. So it gives you an unlimited number of options for your theta and phi. There's infinite options. So this is all the possible positions you can lie on a Bloch sphere. But in terms of algorithms and computing, it would be impossible to use always a arbitrary number of possible gates to apply to your qubit. So we have a set of simplified or special cases for these two general matrices that we use as common gates. The idea of a common gate is kind of like I'm making a metaphor here. Coins is partly convention, partly scientific, that these are the smallest number of coins that we could add up or combine to get any number we want. So that's why all our currency is kind of using, we're not doing 1, 2, 3, 4, 5, 6. We're just doing 1, 2, 5, and then 10, 20, because any combination, a small number of them, can let us get a arbitrary number. But then this is, again, a very simplified version. Here we are only looking at real numbers and is not doing any complex number. We don't have complex money. Whereas in the qubit case, we have a lot more locations, infinite number of locations that state can lie on the Bloch sphere. But then the idea is that we can have some simple forms of these matrices that we can use and combine them to get to the positions we want on the sphere. And that will also mean that it's not continuous, it's discrete. It can put us to a place on the Bloch sphere that's mostly used. Some of the places, just in terms of computing, we're not always trying to get there. So let me give you some examples of these commonly used gates. One set of gates is called the Pauli gate. So Pauli is one of the famous physicists from the 1960s. There are a lot of things named after him. And in the Bloch sphere, we can see that we can rotate around the x-axis, and the Pauli gate x is basically allowing us to rotate along the x-axis by 180 degrees. If your initial state is 0, by applying this gate, it will just flip to 1. And it's the same as the NOT gates in classical case. You're just flipping zeros and ones. So if you can rotate around x-axis, you can also rotate around the other two axes. So for example, y-axis, and then also the z-axis around, so the z gate and the y gates. The I and minus signs here are just phase that's added. If you do the maths, if you want to use the matrix, generalized matrices, and try to apply a particular angle like 180 degrees and check these out, you will end up with some phase factors added in them. So y is rotating around y-axis, and z gate is very commonly used. It's just rotating here. You don't actually change the qubit other than adding a phase there. And this is also redundant. We actually just need x and z, the two gates, in order to get a y gate. So you don't have to actually use y. So if you don't believe it, try to calculate it, apply a z and x in series, and then see if you can get this matrix out. And here is again to show you graphically how x is rotating around z is changing phi. And then z is rotating around z-axis and changing phi, and x is rotating around x, changing theta. And I would highly encourage you to, I told people to bring paper and pen to this class to check if this is the case. Just try a matrix multiplication and see if this is the case. And I hope that everyone has paper and pen by their desk. I would be surprised if you don't have it on your computer, on your desk. Another very useful gate is the Hadamard or H gate. Hadamard is again a person's name. Is a 2x2 matrix that has square root of 2 for all the elements, and they're almost so the quadrants are almost identical, except the last one has a minus sign here. So I would like to have you guys try to do this matrix at a multiplication onto either the 0 state or the 1 state. Just try it out to see what you get. And do people still remember how to multiply matrices? You can comment here in messaging. Just reading messages here, see if there's something. Okay, I can answer some questions as you guys try it. So first one from Bob. The equation makes 0 and 1 vectors look orthogonal, but the sphere shows them, yeah, so they're on the pole. So don't consider the Bloch sphere as any geometrical representation or any physical geometry of anything. And also don't think about as a physical qubit that's actually flipping. It is just a mathematical representation for you to visualize it. And yeah, Anna also commented on that, thank you. When you say gate, is it the amount of voltage that applies? No, it's a different type of gate. So this is a common conventional naming after the classical logic gate. This is a quantum logic gate, which is just a operation that you apply to your components in your algorithm. So it has nothing to do with voltages, although it does. It actually, yes, in some sense, if you build a certain type of hardware that uses voltage to control the qubits, then it is dependent on the voltage, but it's not like a one-to-one mapping to your physical circuit and algorithm. So I'll get back to these. Let's review the answers. I hope you guys get finished. So what I expect you to do is to do this matrix application to the vector. If you start with 0, then you should get this vector out. So that's putting 0 and 1 in equal probability. And we call this, we simplified it as a plus sign. It's a new state. If you use 1 as your initial state, then you will get, again, equal probability, but with a minus sign. And as we previously talked about amplitude, that they could be plus, minus, or even complex. So these are two, again, polar states. And if you represent them on the Bloch sphere, they are in between the 0 and 1 state. And it's pretty intuitive that you're just changing the axis from here to this one. And in a way that you could say that if you start with a classical 0 and 1 case, then the Hadamard gates could put your system in a quantum mechanical case when 0 and 1 are in superposition. And here are some other commonly used gates. They are all derived from the Z gate. They're just a subset, and they can rotate around the Z-axis by different degrees. So these are all for single qubits. And I wanted to show that the Bloch sphere, when you first learn about this quantum gate and manipulation of qubits, is an easy tool for you to visualize what's happening to your qubit. And here is a short video from IBM a long time ago. They were trying to show that in terms of bits, you only have 2 options, but then in the classical, in the quantum bits, then you will have all these different options that could be represented on Bloch sphere. But we already see that we're already using a 3-dimensional object to visualize these this 2-by-1 vector. If you had more qubits, that would be multi-dimensional. And as humans, we wouldn't be able to visualize it. So this graph here is trying to put a 5-qubit into a sphere, but this is a multi-dimensional sphere, so it doesn't actually help us. So Bloch sphere is a nice representation when you're only using single qubit. But then if you scale it to multi-qubits, it's not going to help. So that's that. And when we go to multiple qubits, we will not be using Bloch sphere anymore, unless you're looking at them individually. So a gate or quantum operation is just a matrix that you can apply to your qubit, which are represented as vectors. There's no requirement of how the matrix looks like, except it needs to be unitary. So those of you who study maths would know what unitarity means. If not, here is the definition, but don't worry about it so much. Why do we need gates to be unitary. That's more important. Is because we need to make sure that the quantum gate is reversible. Having matrices being unitary allows it to be reversible. And what does it mean? It just means that when you apply your gate to your qubit, and when you do a reverse of it, and you could reverse back to where you started. So unitarity guarantees your matrix to be reversible, and also that could allow the probabilities to add up to 1. And the reason, the definition of unitarity is basically is called is a dagger. Dagger means the complex conjugate transposed, and if you time these two, you will get the identity matrix, and that's all it means. That's unitary. So you can try this math later if you like. Okay, so we have like 8 minutes left. I do want to point to you where you can have more understanding of gates. So you can actually get hands-on with these exercises we developed at Microsoft. So this is a set of katas that you can use to try learning these concepts we talk about.